Okay, so we're in 2.2 now, and we're going to be discussing Venn diagrams and subsets. So the first thing that we need to talk about when it comes to sets, now that we've gotten some of the basic terminology and symbols under our belts, is the concept of a universal set, or a universe. So the idea here is that when we're talking about a specific type or a specific set, there's usually an implicit assumption regarding where that set lives. So I'm going to illustrate this with an example. Suppose we're looking at this set here. And again, this is in set builder notation, which takes a little bit of getting used to, but just read the way that we read these sets, this says that S is equal to the set of all x such that x is greater than 1. Or in other words, it's the set of all numbers that are larger than 1. Now, think of some of the sets we looked at back in 2.1. Sets can contain literally any element whatsoever. They can be numbers, they can be letters of the alphabet, they can be days of the week, they can be ideas, shapes, they can be literally anything that's an object can belong to a set. However, a number of those things would not make sense to be considering in the context of a set like this one. So here's what I mean by that. What we want to do is define something called a universal set, or sometimes we simply call it the universe. In a more broad context, like with formal logic, which we study in chapter 3, or in philosophy, the same idea is called a universe of discourse. But the idea of a universal set is to basically have a larger set that we can pick elements out of and compare to a particular set to decide whether they belong there or not. So here's what I mean. For this example, again, we're looking at the set of all x such that x is greater than 1. I want to consider a universal set, which in this case turns out to be the set of real numbers. Why real numbers? Well, real numbers are numbers that I can compare in a meaningful way to the number 1 and decide whether they are larger than 1 or not larger than 1. So for example, the number -3 is a real number. Does it belong to this set S? Well, the answer is no, because -3 is not greater than 1. I can compare it to 1, but it doesn't satisfy this defining condition for elements of that set S. So I would say that no, -3 being a real number does not belong to that set because it's not greater than 1. 5 is a real number. Does that number belong to S? Well, in this case, yes, it passes that condition. It's comparable to 1 because I can say that 5 is greater than 1, and that satisfies that condition, putting it in the set S. So now consider something that's not as reasonable to be comparing to 1. For example, Tuesday, the word Tuesday. You wouldn't look at this set and ask yourself, I wonder if Tuesday belongs to this set, because that's plainly ridiculous. I mean, you don't, it doesn't make any sense to ask whether Tuesday is greater than 1 or less than 1. So we would say that the word Tuesday, or the day of the week Tuesday, doesn't belong to the universe or the universal set that this set is thought to live in, because it doesn't have any meaningful comparison to the defining condition of this set, then whether it's greater than or less than 1. Greater than or not greater than 1, I should say. So that's a little bit abstract, a little bit vague, and fortunately for us, we don't have to deal with universal sets in this kind of implicit way. Usually in set theory, the universe or the universal set is implied. So here, notice if all I gave you was this, S equals the set of all x such that x is greater than 1, nowhere in this description did I say, consider this set within the larger universe of the real numbers, or within the universal set of the real numbers. It's just kind of natural to assume that the real numbers are the universal set. It's the set that these objects ultimately belong to. But that can be very difficult to decide what is the natural choice for a universal set. So throughout this section, we're going to be defining the universal set for you, for those comparison purposes. And to that end, I also want to say that even though this discussion sort of shows that the set of real numbers is a natural choice for the universal set that would contain our set S up here, it's not a necessity that we make that our universal set. The universal set can be chosen either in a natural way or in a completely arbitrary way. I could have said that the universal set in the example up above is the set of all positive real numbers, leaving the negatives completely out of the question. That's a valid universal set for this because everything in S is a positive real number. So the main thing is that the universal set that we're working with has to be something that contains everything that belongs to any set that we're working with. It has to be larger in that sense. Okay? Again, this might feel very vague and abstract at this point, and we're going to do some work to make that a little bit more concrete. So don't worry if this is confusing right now. It should start to make a little bit more sense as we work through examples and look at this a little more deeply. Before we touch on any examples, what I want to do here is look at kind of the main reason we care about a universal set. Because you may be looking at this and think, well, what purpose do we even have behind talking about this universal set? The reason we care is because it allows us to define these things called complements. Oftentimes, and this is really, really common in statistics and probability, but plenty of other fields as well, if we're given a set of objects, it would be of value to us to define another set containing all of the other objects that don't belong to this. So this is the definition that we're going to work with. If A is some set within a universal set, U, remember U is supposed to be the set of all objects that we would consider in that particular example, then we define the complement of our set A as follows. Notice we use this little apostrophe right here, but we read this as A complement is the set of all X such that X belongs to the universe U, but does not belong to A. Okay? So let's illustrate this with an example. In this example, I have this sort of arbitrary set that I'm defining to be my universal set U. So 1, 2, 3, 4, 5, 6, these are the set of all objects that we would ever consider in this example. And then we're going to let A be the set 1, 5, and 6, or the set containing 1, 5, and 6. And we're also going to let B be another set, and we're going to define it to be the set of all even numbers in U. So notice that both A and B only contain elements that come from U. And that should be the case anytime we're working with a universal set. No sets that we work with should contain anything that doesn't belong to the universal set. This is supposed to be all that we know in this example. We're asked to find A complement and B complement. Now, in a case like this, where we've explicitly laid out exactly what belongs to our universal set and exactly what belongs to the set A, it's very, very easy to find A complement. All we're doing is we're looking in the set U for all of the elements that are not in A. So A contains the numbers 1, 5, and 6. If we eliminated those from the set U, that leaves us with the numbers 2, 3, 4. So that means A complement contains 2, 3, 4. Notice that it's a set that only contains elements from the universe U, but it contains everything that's in U that you can't find in A itself. Okay, so A and A complement you can also look at as two parts that can go together to create the universe, but they have no overlap. We'll look at that in more detail in a later section when we talk about intersections and unions. B is given a description without listing the elements, but I can list the elements of B pretty easily. B is the set of even numbers in U. That means it's the numbers 2, 4, and 6. Those are the only elements in U that are even numbers. So that would mean B complement is the set of all odd numbers in U. That would make up everything else. 1, 3, 5. Okay? Fairly straightforward. Now, in the title of this section, we mentioned something called Venn diagrams, and it's pretty likely that you're at least somewhat familiar with the idea of what a Venn diagram is. We use it outside of math all the time for kind of casual comparisons between sets of objects. So I'd venture to guess that most people are pretty familiar with what a Venn diagram is. And we're going to use Venn diagrams throughout this chapter to sort of give a visual representation of the concepts that we talk about. So what I want to do is show how we depict universal sets and sets contained in those universal sets using a Venn diagram. So here we're going to let A just be some arbitrary set that's contained in this universe U. And I want to create two Venn diagrams, one for A and one for A complement. So here's going to be the one for A over here, and the one for A complement I'm going to put over here. With a Venn diagram, when we're talking about a universal set, the universal set is going to be depicted by a rectangle like this, and we name that universal set in one of the corners. So I'm going to say that my universal set U is this rectangle. Now the job of a universal set or a universe is to contain all of the elements that we're allowed to talk about in a particular example. So if A is a set that we're considering, then all of A needs to be contained in this universal set U. So I can write A this way. And I need to put the letter A in there somewhere to indicate that that's what that set represents. Okay? Now, not only that, if you read the sentence up here, we're going to use shading to indicate which parts of the universe we're considering. So if I wanted to create a Venn diagram for the set A, and A is everything within this circle, then I would shade in this circle and say, see that shaded part? Everything in that shaded part represents the set A. Okay? How then would we create a Venn diagram to illustrate or visually depict A complement? Well, notice I'm going to do essentially the same thing I did in the first problem. Notice I'm not calling this circle A complement. I don't want to do that. I only want to work with this set A here. And the reason for that is because I want to see in my visual depiction here, my Venn diagram, how A complement relates to the set A. Well, remember, A complement by definition is the set of all elements of my universe that are outside of A, that don't belong to A. So as a Venn diagram, I can illustrate that by shading in everything that's in the rectangle, so everything that's in the universe, but is outside the circle. So you can see these as, in a certain sense, opposites, or, as the name implies, complements of each other, these two Venn diagrams. We do a lot more with Venn diagrams in the sections that follow, but this will get us kind of a good start there. Now, one really interesting thing that we start to look at in this section is how the empty set fits in with these definitions, specifically with complements. So remember, the empty set, which we use this symbol for, a circle with a slash through it, we define that to be the set containing no elements whatsoever. Now, if we're working within a universal set U, then what is U complement? Well, I'm not going to create a Venn diagram for this because it wouldn't really be as illustrative as these examples are. But by definition, U complement should be the set of all elements that are in the universe, but are also not in the universe. Now, that sounds a little paradoxical, but the reason for that is because there are no elements that can satisfy that. There's nothing that can live within your universe and simultaneously not live within that universe. So that would imply that there are no elements, there's nothing in the complement of U. Or equivalently, we could say that the complement of U is equal to the empty set. Looks like there's like a little comma here. That's not supposed to be there. Okay. Now, by the same token, what is the complement of the empty set? Well, remember, by definition, this would be the set of all elements that are in the universal set U, but are simultaneously not in the empty set. Well, the empty set, again, it doesn't contain anything at all. So everything that's outside of the empty set would simply make up the entire universe U. And that means the complement of the empty set is our universal set U. Okay? Now, we're moving on to the next part of this section, which is the idea of a subset. So let's get into that. So far, in the examples that we've looked at, specifically let's look at these Venn diagrams. We've been working inside a universe, and we're only really considering one set within that universe. as well as its complement. But what if we took two different sets within a universe and we wanted to compare them in some way? One way of comparing two sets is determining whether or not one set is a subset of the other. Now that there's probably some intuition when I say subset. You probably have an idea of what I'm talking about, and your intuition there is most likely correct. But we do need a mathematical definition for subset so that we can use that in applications like this. So let's get that definition down. We're going to say that A is a subset of B, and we use this notation. It says A is a subset of B. It looks like a sideways capital U with a line under it. That says A is a subset of B, and what this means is that every element of A is also an element of B. There shouldn't be... Oh, yeah. I was going to cross off that if, but that does belong there. That does belong there. Okay. Symbolically, we could say the same thing this way. For every x in A, we have x in B. Or for every x that's an element of A, x is also an element of B. Said differently, B contains everything that A does, right? So that intuitively is probably how you understand a subset anyways. You just may not have thought of it in those terms. Now, back in section 2.1, we defined set equality. And part of that definition, we said that set A and set B are equal to each other if everything that's in A also belongs to B, and if everything that's in B also belongs to A. So in other words, set A and B contain all of these same elements and nothing else. We can frame that same definition in terms of subsets. So that definition, A equals B, is the same thing as saying that A is a subset of B and B is a subset of A. An important thing that we haven't really mentioned here but follows from this definition is that every set is a subset of itself. And we're going to see that in an example down below. So we'll talk about that once we hit that example. One last thing here before we move on to the example. It may be the case that A is not a subset of B. In other words, A may contain elements that do not appear in B. And in that case, we use this notation, similar to what we did in section 2.1 for elements. If A is not a subset of B, we use the subset symbol and we put a line through it to indicate that it's not a subset. So 4 examples down here. I want to look at each of these sets and compare the set on the left to the set on the right. The goal here is to determine whether the set on the left is or is not a subset of the one on the right. So starting with this first example, the set on the left contains the elements A, B, C, D. Notice all 4 of those elements are also in the set on the right. The set on the right also contains E, F, and G. But the important thing here is that every element that belongs to the set on the left also belongs to the set on the right. That would mean that A, B, C, D is a subset of A, B, C, D, E, F, G. So I can write the symbol for subset showing that relationship. This is a subset of this. Okay? Moving on to part B. Is the set on the left a subset of the set on the right? Well, the first 3 elements of this set are contained here, 1, 3, 5. But that's ultimately irrelevant because the set on the left has 1 element that does not belong to this set on the right. So even though these two sets overlap with the numbers 1, 3, and 5, this is not a subset of the set on the right because the number 9 is not contained here. Okay, so I put that subset symbol with a slash through it. This one's a little bit trickier because we don't get to explicitly see the sets written out in roster notation. We don't have a listing of the elements of the set. So we have to think a bit harder about this one. Is the set here a subset of the set here? Well, this is the set of all x such that x is less than 1. Now remember, we considered this set at the beginning of this video, and we said that the universe of discourse here is the set of real numbers. So really, we consider this to be the set of all real numbers that are less than 1. Is that a subset of this one here, the set of all numbers that are less than 3? Well, in this case, yes. Because think about this for a moment. If I were to pick any element of this set, by definition, that element would have to be less than 1. But if a number is less than 1, then it's automatically less than 3. because 3 is larger than 1. So that would mean everything in this set, all of the numbers that are less than 1 are also in this set, all of the numbers that are less than 3. Now this set contains more numbers in it, or it contains numbers that don't belong to this set. For example, the number 2 is in this set because 2 is less than 3, but it's not less than 1. But that doesn't really matter because everything here also lives in here, giving us the subset relationship. What about here? We're back to roster notation, and I'm checking to see if every element in this set also belongs to this set. Well, X, Y, and Z, those are the values or the elements of this set, and all 3 of those appear in this set. So that would make this a subset. This is a subset of this. Now, there's a couple of things I want to point out about this. First of all, not only is the set on the left a subset of the set on the right, but the reverse is also true. The set on the right, which contains the elements Z, Y, and X, is a subset of the set on the left because all 3 of those show up here. It does not matter that the order is not the same because in sets, order is irrelevant. It's simply a question of, do the things in this set show up in this one and vice versa? So these are both subsets of each other, which means that this set is equal to this one. They contain identically the same elements. Okay, but again, this sort of shows that under our definition, every set, this set in particular, is a subset of itself. Okay, even if that seems a little counterintuitive, that is always the case. Let's do a Venn diagram for this subset relationship now. So I'm going to say that A and B are sets within some larger universal set U, and let's suppose that A is also a subset of B. I want to illustrate this with a Venn diagram. So we start out the same way. Okay, well, we create a rectangle, and we denote that with U. That's our universal set. And then what I want to do is show this relationship. A is a subset of B. So what that means is that if this is the set A, right here, everything that's in A should also be contained in B. That, in a sense, makes B a larger set, potentially. Remember, B can also equal A, but we don't know that to be the case here, so we're not going to assume that. All we know is that everything that's in A is also in B. And in a Venn diagram, we illustrate that by having the set A completely contained inside the set B, with both sets still being contained entirely within this universal set U. Okay. Now, I'm not shading anything here because the goal was not to visually depict a specific set, but rather show a relationship between two sets. So this is one of the rare cases where we're not going to bother shading anything because that's not really relevant to what this is supposed to represent. This is where I'm going to stop this first video. We'll pick up where we left off in the next one.